Thank you, everybody, for being here. Today we have the pleasure of having Professor Claus de Castro Aranha with us, which will deliver a brief talk that as you can see here, it's Evolutionary Frankenstein from Metaphor Heuristics to component research. So, Professor Aranha is now with the University of Tsukuba in Japan. We have to thank him and not just for giving the talk, but for giving the talk at such an high hour in Japan at this time. But has been so kind to adjust, and we are most grateful for that. Professor Aranha is a very well-known researcher in the area of evolutionary or inspired algorithms and complex systems. I think that the talk that he's going to give today is going to cover quite a few of those topics that he's researching with. And I'm confident that you will find it very interesting because it's just tied very nicely to some of the things we are been looking lately in our course. So I don't want to take more time for the talk, so I just hand it over to Claus. So please, you can start that if you wish. Claus, thank you.
Thank you. Thank you very much, Carlos. Thank you for the kind invitation. Hello, everyone. And I'm really happy to be here to talk with you. We had some very nice talk with Carlos before, especially about the middle of the talk. So today, he told me that it's like an introduction lecture to evolutionary computations. So today I want to go into one of the topics that I have been very, very excited about recently, which is this part of components research. I'm getting a little bit of feedback. Maybe someone here has an open mic over there. Okay, now it's better. Fantastic. By the way, if my voice is strange or if anything is weird or if you want to ask any questions, I'm looking at the chat as I talk. This is one of the advantages of doing this online. So feel free to write your messages on the chat. All right. So first, let's do a very quick self-introduction. So like Carlos said, I'm Claus. I'm actually from Brazil. I've been living in Japan though for a long time. This year is actually the year that I have been living as much in Japan as I had in Brazil. So take from that whatever you want. And one thing that I think it's very related to this lecture is that I love programming. And for me, what is so cool about programming is the ability that you have to recombine words to make anything. And that's one thing that I'll talk over and over in this lecture, is about recombination. And also, of course, you can use programming to calculate things, visualize things, compile things. And what I really like to do is like games. I was just programming, doing some game programming before starting this class, and from games you can do art and art life. So one research that I worked that I will not talk about today is about artificial life. If anyone is interested in that, maybe ask some questions on the question part. So my research is artificial evolution, which is the topic today, and artificial life. So let's talk about that. Oops, I have to click here. Okay. Fantastic. So the topic of the talk today, and I'm going to talk about a little bit less than 1 hour. I plan to maybe talk about 40 minutes, 50 minutes, and have some time for questions of everyone. But the topics, how do we use evolution to design algorithms? So that's evolutionary computation. But the message that I want to talk about is that through careful study and recombination, and by that I mean to mixing everything, shaking a lot, we can do some very cool algorithms. So the topics I'm going to talk about is, we're going to start about what is evolutionary computation. I'm not sure how many people are new to evolutionary computation, so I want to start slow. Then I'm going to introduce a few classic evolutionary computation algorithms, and then I'm going to talk about a lot of weird algorithms. And then I'm going to mix the weird ones with the classic ones and discuss how we can put them all together to make more interesting things. So let's start with part one. Quick reminder, quick review of what is evolutionary computation. So what is evolution? Why evolution? Well, the first idea is that evolution by nature is, well, frankly, amazing, right? We look at nature and we see all sorts of creatures. This figure on the right is a crab that lives under the sea. I don't know about you, I never saw a crab that has gloves like this. This is funny and amazing, right? And there are all sorts of weird creatures, like all kinds of spiders and mammals and birds and insane stuff. And then we got like the microorganisms. I don't know if you heard of like ants that colonize other insects and take over their minds, or we have birds that use tools to open fruits. We have mammals that change rivers. So all sorts of very strange organisms. One thing about them is that they are well adapted to the environment. Okay? And one thing is that, for instance, this crab did not think, oh, I'm going to live in a cold place, so I'm going to have like these things on my hand. No, it was the other way around. It developed like this to adapt to its environment. So the creatures in nature, they react to the environment. They don't use the knowledge from the environment to adapt. So we ask ourselves, can we do the same thing to computer systems? Can we create computer systems that adapt to all sorts of problems? That's the question behind evolutionary computation. As you know, evolutionary computation actually has like over 50 years of story, right? And the idea that after 50 years, we have a very good framework about how to do artificial evolution in a computer. The idea is that we define a problem as the environment, and then we define the solution as the individuals. And the individuals will adapt to the environment, which means that the solutions will get closer and closer to the answer of the problem we try to solve. Now, the key for this is to evaluate the individuals for the quality to the environment and call this the fitness score. And then we reproduce and modify the individuals based on the fitness. So these four rules are the basis for evolutionary computation. Evolutionary computation has been used for a lot of stuff. I'm pretty sure that you heard some of this. I'd like to highlight these two examples. So here on the right, we have the bullet train in Japan, the N900, that the shape was developed using evolutionary computation. On the left, I have one example that I really like, which is an antenna used for artificial satellites. The shape of this antenna was also evolved using evolutionary computation. Now, why do I really like this example? This is one of the things that I like the most about evolutionary computation, which is the solutions are not the same kind of solutions that humans think. Like if you ask a human, create an antenna, they will never create this. This is like so crazy, like it goes everywhere, it turns around, it looks like a little bit of trash. But evolutionary computation does not care. It creates something crazy, and that's the best thing about it. Just to go a little bit on our side, a lot of people are talking about AI art. And AI art will replace human art, or AI art will not replace human art. To be honest with you, I think that the art that is done by modern machine learning, OpenAI, etc., is boring because it tries to imitate human. If you go to art from evolutionary computation, it was crazy. Like maybe 7 years ago when they started doing that, they had like artificial neural networks that generated images with eyes everywhere. So things that are done from the computer, they are cool when they are not human, when they are crazy. And I think we should put more effort in that, more effort in the crazy. Anyway, So the cool thing about evolutionary computation is that it can be very different of how a human thinks. So let's keep that in mind. So why does it work? Okay, I said, okay, a lot of people use evolutionary computation for trains, for art, for satellites, but why? Why does just mixing things work? So we define more mathematically evolutionary computation applied to an optimization problem, where the optimization problem is that we're trying to find a vector x in a multidimensional real domain that minimizes the value of some function f of x. Now, this works by testing several solutions. What evolutionary computation is doing is just trying one after the other solution. This is called search-based optimization. Search-based optimization is different from numerical optimization, that we're not calculating the solution, we are testing different solutions. It's like when you're looking for your keys in the house, you're looking here and there, you're not calculating where the key is. You're just looking in different places. The cool thing about SBOs is that they don't depend on a gradient. So they work for some very particular problems, like discontinuous problems. They also don't require domain knowledge, which was something that I said before about evolutions and animals. So it's a general method we can apply to any sort of problems. So these are the things that make evolutionary computation work really cool. Of course, it has some disadvantages. It is slower. If you know how to calculate, search is always slower than calculating. But if you don't know how to calculate, then you want to search. Also, one thing about evolutionary computation is that it's very easy to program. So you can program evolutionary computation methods very easily. You can understand the program, and they are very easy to parallelize. So I find it really cool. I give like my new students some very easy evolutionary computation programs to do, and that's something that I enjoy. Let's see how easy this is. So the oldest evolutionary algorithm that is still used today are evolution strategies. Evolutionary strategies come from Heisenberg and Sheffield, 1971, so 50 years ago, well, more than 51 years ago. And what is the idea? The idea of evolutionary strategies is that we're going to have a parent that will produce an offspring, and then compare with the offspring, and if the offspring is better, keep the offspring. If the offspring is worse, keep the parent. Okay? Very simple idea. The offspring will have a mutation. So for instance, here, x0 is the parent. x0 generates 3 offsprings. And then this one, x1, is better than x0, so it replaces. Now, x0 generates 3 offsprings. x2 is better than x1, so it replaces. If x2 is not better than x1, x1 continues, and we generate 3 other offsprings. And that's it. That's the algorithm. We can see the entire algorithm here. We start with an x belongs to our multidimensional space, and then we have a number of offsprings, which is a parameter, lambda, and then we have a step size. So until we decided to finish, we repeat. We generate a number lambda of offsprings. Each of the offsprings has a normal mutation, just a vector of numbers between -1 and 1 with variance 1. We multiply that by the step size, and then we test to see if any of them is better than the parents. That's the algorithm. You can program this in like 5, 10 lines, and you're done. You have your evolutionary algorithm. Some modern versions change this S to be adaptive or to use covariance, but the basic idea is the same. Now, this was the very first one, the one that most everyone thinks when they think about evolutionary computation are genetic algorithms. Now, what are the genetic algorithms, and what is the difference between genetic algorithms and evolution strategies? The key idea of evolutionary algorithms is that instead of having one parent, we have a population. A population means that we have several solutions that we're testing at the same time. So the search is in parallel. Now, the idea is that we want to bias this set of solutions to find the good solutions, to find a good solution to our problem. So we use a crossover, which means that we get two solutions and we exchange one part of them. Now, the idea is that if this part that we exchanged is a good part, is part of our solution, it will improve the fitness of that solution, and that little good part that we exchange will multiply through our set. This was called the schemata theory. There were a lot of people that studied this theory. There are still papers about this schemata theory. But the key idea is that we get because the solutions are in parallel, each of them may have a small part of the answer, and they exchange this small part of the answer between themselves, and that improves the result of the genetic algorithm. So here we have, traditionally, genetic algorithms use binary representations. There are some variants that don't, but let's consider the traditional one. So we have a binary representation of our solution, and we have our population, which is now a matrix on the binaries. And then it's very similar to evolution strategies. We evaluate all the solutions, then we select two of the parents at a time, we exchange some part between them, and then we do some mutation, and that is now our new individual. And then we replace the entire population here, okay? So that's the basic idea of the genetic algorithms, and in the end, we try to find the best one. Okay, let's go to a different one. This is differential evolution. Differential evolution is a little bit more modern. It was done in 1997, so about 25 years ago, I think. Differential evolution is a very good SBO. It's still very competitive. There are methods that are a little bit better, but if you want to do a quick and dirty evolutionary algorithm and you don't care about learning too much about evolutionary algorithm, I usually recommend start with differential evolution. It will give you a reasonably good result, and it's reasonably simple to implement. So what is the idea of differential evolution? Well, differential evolution is a variation on evolution strategies. So we get a parent, we do a mutation, and we get an offspring, and then we compare the two. Like GA, it has a population at a time. So it has a little bit of evolutionary strategies, a little bit of GA. Now, the key idea of differential evolution is how we do the mutation step. Instead of just getting like a normal distribution and calculating the mutation step from there, the mutation step here is calculated based on our population. So you can see here, to calculate the mutation step, we have this part here. We choose 3 random individuals. And the first time you read this, you say, well, why do I choose 3 random? Why don't I choose the best or the worst? There's actually a reason for them to be random. Then after you choose 3 random, you get the first one, and you subtract the 2 second ones. And you can see here, like, this is the subtraction. We're subtracting xb by xc. So we have this vector here, xb minus xc. And then we add that to xa. So here's xa plus xb minus xc. So it's this mutation vector here that generates a candidate. Then we do a crossover between the candidate and the parent, and that's our new solution. Why is this so good? Well, the reason why this is so good is because by doing this subtraction between 2 random solutions, what we are actually doing is that we are taking a sample vector that the size is proportional to the spread of our population. Which means that the really smart thing about differential evolution is that it automatically adjusts the size of the mutation depending on how spread our population is. So in the beginning of the search, the population tends to be very spread, so the mutation vector will be very big because we're searching all over the place. When we start to find the best solution, the mutation vector will start to get smaller and smaller and smaller, automatically, without any parameters. So this is what is really cool about differential evolution. A very smart method, which is very simple to program. It's just this. You can write this in Python or in C or your favorite language in 30 minutes. And then you get a very effective optimization method. All right, let's go one more before we finish this quick view. The last algorithm of the algorithms that I consider like representative of classic evolutionary computation is particle swarm optimization. Particle swarm optimization was proposed by Dorigo in 1992, and the basic idea, it's well, some people say it's not evolutionary, it's swarm, it's swarm intelligence, but it's still a search-based optimization. I put them all together, and you're going to see why I put them all together later in this talk. But the key idea here is we have, again, a population of solutions, and we are checking all the solutions at the same time. Now, the key difference between particle swarm optimization and all the other algorithms that we've seen so far is that the solutions in particle swarm optimization have a state. All the others, the solutions were stateless. The only information that you had were the parameters of the solution. But here, besides the parameters, each solution also has a speed. So you can imagine that each solution is like a particle that is walking. So one solution begins here, and then it walks here, and then it walks here, and then it walks here. So the solution has a speed, and that speed will move the solution across the problem, searching for the best answer. Now, how is this speed calculated? This speed is calculated following this algorithm here. So basically, for each particle in our population, we update the speed where speed of I is equal to the speed of I plus a weight that we can, there is a small random factor here, not very important, but a small parameter. But the first weight is, oh, there's a plus here that I forgot. Sorry, I need to fix this slide later. So it's the speed plus the personal best, which is the best solution that this particle has found until now. So for instance, if the personal best is here, the personal best vector will be pointing this way, okay? And then the global best. So if the global best is here, the global best vector will be pointing this way. So our speed becomes the old speed plus the global best times some weight plus the personal best times some weight, and this gives us our new speed. Okay? So why is this cool? The cool thing about particle swarm optimization is that because of this speed movement, the particles are kind of independent because each of them has their own speed, each of them has a personal best, but they are also connected through the global best. This means that they have independent information and they exchange information like GA, but they also have independent information. And because of this speed, particle swarm optimization is very good when your problem requires you to track not one answer, but multiple answers at the same time. This is usually called a niching problem. Particle swarm optimization is also really cool if your answer changes over time. So as your answer changes, because your particle has a speed, it keeps moving together. Okay, so I went a little bit long on this, but why did I explain all these algorithms? Because each algorithm has a different idea. Each algorithm has a different good thing about it. So we have a comparison between exploration and exploitation. Exploration means explore many new ideas. Exploitation means improve the idea. We have parallel search like in GA versus collaborative search like in PSO. We have sequential search versus sampling. We have how to escape local optima. So there are many characteristics in the algorithms, and the ideas that we put in the algorithms will say if the algorithm is good at this idea or that idea. Okay, now we get into part 2, the rise of the metaphors. So I talked about 4 classic algorithms. By the way, if anyone if anyone has any questions, write the questions on the chat. If we have time at the end, I'm going to read the questions and we can go back. So if you have questions, keep writing them on the chat. We can talk about them later. Okay, let's see 2 more algorithms. Artificial bee colony, developed in 2005. We have a population that is divided between worker bees, onlooker bees, and scout bees. And in the paper, it's written that the worker bees find food, evaluate the closest nectar, and dance. Okay? Bees dancing. Cool. And then the onlooker bees, they look at the dance, and they go to the closest source. And then the scout bees replace the abundant food sources with new sources. I don't know what's the relationship between scout bees and dances and sources, but I'm pretty sure the paper explains everything. And then we have Cuckoo Search. Cuckoo Search 2009, only 12 years ago. So we have a cuckoo that replaces the solution using Levy flight. And Levy flight is basically Levy distribution mutation. And then we choose a random nest and we replace it with a new solution. And then we abandon a fraction of the world's nests. I don't know exactly what are the relation between the nests and the cuckoo. And I hope that you can notice that there is a difference between these algorithms and the others that I explained before. The difference, the difference, what is the dance? Okay, so are the bees, is the dance the solution? Are the bees the solution? Is the nectar the solution? Which one is it? Okay, so the ABC description also does not mention that one big difference in ABC, if you actually read the paper, the code, one big difference is that the mutation in ABC only changes 1 dimension at a time. Now, in CS, we read the paper, and if you read the Cuckoo Search paper, you get a very big question. Is the solution the birds or the nests? Sometimes it seems that the solutions are the birds. Sometimes it seems like it's the nest. So it's a little bit mixed. And then if you read both papers together, you notice that scout bees and abandoned nest, they are actually the same thing, but they have different names, and it looks like they're doing different things. So what's the problem? The problem here is what I like to call metaphor heuristics. Metaphor heuristics is when the metaphor, the birds, the bees, or even the genes, the particles, when the metaphor is more important than the algorithm. And that's the problem. Now, ABC and Cuckoo Search are still kind of okay-ish algorithms. There are some people that really hate them. There's much, much worse. So I keep this list called the Evolutionary Computation Bestiary of lots of metaphor algorithms. So between 2000 and 2005, we have antibodies, we have musician algorithms, we have bacterial algorithms, we have queen bees, fish, frogs, nuclear collision, and wasps. Is that enough? 2006, we have weeds, worlds, bee colonies. This is a different one. It's not the same as the one that I explained. There's monkey algorithms, imperialism algorithms, parliamentarism algorithms. 2009, we have geography, fish, worms, fireflies, group counseling algorithm, whatever that means. 2010, wind, brain, ecology, electrons, cats, galaxies, mosquito algorithm, teacher algorithm. 2014, soccer algorithm, raindrops algorithm, grays, wolves algorithm, worms algorithm, zombies algorithms. I love the zombie algorithm. Not over yet. 2017, we got duelists, FIFA World Cup algorithm. I wonder if they have the 2022 edition. Virulence algorithm, water whale algorithm, yin-yang algorithm. So it's crazy, like millions and millions, over 200 algorithms. Oh, there's more, like here is until 2020. There's orca algorithms, whales algorithms, mayflies, student algorithm. We have the teacher algorithm, now we have the student algorithm. Soccer style algorithm, bison algorithm, Bruce's algorithm. Ooh, yes. So there's a problem here. I hope you will see that there is a big problem here. Like in my website, we have over 200 algorithms. Some people collected a few more than over 300 algorithms. And the question is, are really there over 200 ways to do search-based optimization algorithm? The answer is yes, but not in this way, okay? Is it really the right way to organize these using these metaphors? What's the problem here? So what's the problem with metaphor algorithms, okay? The big problem with metaphor algorithms is that when we start to abandon the programming part that is super cool, and we start to use like all these sorts of animals and humans and fairies and monsters and political systems and disease, we start to lose track of what is really going on. So here are some parts of the papers. Like, look at this. Tell me what this algorithm means. The amount of soil in the edges of the iteration best solution is reduced based on the goodness of the solution. Amount of soil. The selection of two barnaids is based on the length of their penises. Okay. The objective function was regarded as invariant for the reference frame, something like a transcendental entity in space-time. Mind blow. So yeah, we have a problem here that I don't know if this is the same thing, it's different thing, I don't know what this means. And for 200 algorithms, okay, so to summarize the problems, the literature becomes flooded with algorithms that are identical or very, very, very similar. And these papers, they don't have good reproducibility. Like, if you think that the description is bad, the experimental section is even worse. And we who are computer scientists, we already have different difficulty parsing which ones are the good and which ones are the bad. People from outside, engineers or mathematicians, people who don't really understand this part of evolutionary computation, they cannot really tell the difference. So there are a lot of these people use these metaphor algorithms to hide suspicious activities like Siamese science, when you get like a research and you cut it in very, very small parts so you can have lots of papers, or citation rings. There are some citation rings in the metaphor family, but sometimes it's just because people are really excited but they don't really know how to do about that. The problem is, a paper using purely metaphor language with no scientific standards will be non-falsifiable. It will be difficult to tell if the algorithm is good or bad because I don't know what the whales have to do with the black holes and the cats and the zombies. Fortunately, things have been changing in the last like 4 or 5 years. There has been like the biggest explosion of metaphors was around 2010, 2015. I think we're starting to push back on that. So Kenneth Sorensen in 2015 wrote this paper, Metaphor Heuristics, the Metaphor Exposed, which kind of discussed all this problem that I was presenting to you. And then we had Villalon and Wayland doing analysis of individual metaphors that were very popular and showing that, like, if you take away all the metaphor, if you take away the zombies and the cats, it's just evolution strategies with a different parameter. Or it's just particle swarm optimization with a different formula. So why don't you publish the paper as particle swarm optimization with a different formula? Questions. Recently, we published a paper with over 50 people signing, which is metaphor-based Metaphor Heuristics, a call for action, asking for journals to try to help us not accept these kind of metaphor heuristics, and it has been working. Some journals like Operation Research, Some Intelligence, Tello have started to work on this. Okay, but there's this question. Is it a bad thing to create new meta-heuristics? So we go to part 3, component-oriented evolutionary computation. So we don't want to create thousands of new algorithms, but sometimes we need different algorithms. Okay, sometimes we need to have a specialized meta-heuristic for a specialized problem. For example, Problems with different numbers of local optima need different strategies. Problems that are multimodal need different strategies. Separability of parameters require different strategies. If the problems have some characteristics like they are dynamic, the optimal change over time, or you have multiple objectives, or you have constraints, you need to adapt your algorithm to these problems. So new algorithms are necessary. Okay, and there are even new problems that we have not met yet, so we still need new algorithms. The question is, how do we do that in a responsible manner? And the answer from that comes from software engineering. We need to go back and say, okay, programming is fun, but let's try to program a little bit more organized. Okay, and this is the composition approach. The idea of composition approach is to reuse the knowledge that already exists. We get components of the algorithms and we mix and match them. Now, if we look at search-based optimizer, in the beginning of the talk, I said they have a common structure. We generate solutions, we test the solutions, and we modify the solutions. If you look at all the algorithms that I talked about in this talk, and I talked about a lot of them, all of them have the same structure. But we can change this structure with some tricks. Like we can use the mutation from evolutionary strategies, or we can use the crossover, or we can use the velocity. We can even use the techniques from ABC. So we can use, for example, the idea of using restart of solutions, which are the scout bees. The scout bees are just regenerating parts of the solutions. Or from Kuka search, we can use the Levy distribution to do mutation. Doing mutation with a Levy distribution is actually pretty good. But instead of saying, okay, we have a brand new algorithm where we have birds that fly away and drop eggs, and then they go back to the nest and they sink to the zombies, we say, no, we had particles row optimization, but we add a Levy distribution-based mutation. And when I say that, it's much easier for you to understand how my algorithm is different from PSO. That is the compositional approach. We don't create new algorithms, we create new components, and we create the algorithms based on the components. Welcome to the magical world of compositional algorithms. We break the algorithms into parts, and then we mix them together, and we create the Frankenstein. Actually, it looks a little bit more like this. So we have lots of algorithms that have been designed by humans. We look at those algorithms, we study them, and we identify what are the good components. We put all the good components of these algorithms into a component library. Then we used another recombination system, and there are many different recombination systems. I'm going to talk about a few of them here. But we use a recombination system to put these components together that will give us an algorithm configuration. And if any of you like machine learning, you might have heard of AutoML. This is very similar to AutoML, but this comes before AutoML. But because there are two parallel systems, two parallel fields, people don't, sometimes they see the similarity, they don't see the similarity, but this is very similar to the idea of AutoML, but for evolutionary computation, okay? And then we generate specific algorithms for specific problems. But these specific algorithms are just recombinations of components that we already know. Okay, so how do we compose this algorithm? Like I said, there are many different ways to do the composition of the algorithm. One of these ways is very simple. We treat the components as parameters. So, for example, in differential evolution, we have two parameters, CR, which is the crossover rate, and F, which is the multiplication of the differential vector. Now imagine that we add another component, another parameter, which is the formula that we use to calculate the differential vector. Now our formula is also a parameter. And the options of that parameters are different ways to calculate the mutation step. We can use the differential vector, we can use Levy flight, we can use normal mutation. Now our algorithm is compositional. It's D, but we can change some parts of the D. There's a very nice paper from Bezerra and other authors in 2015, automatic component-wise design of multi-objective evolutionary algorithms. They do exactly this for the multi-objective domain. So if you're interested in this, I really recommend starting from this paper. Maybe there are some earlier papers. I think this one is very approachable and very complete. Me and Felipe, oh, sorry. One big problem of this approach is that coding actually becomes a little bit more complicated. So in the beginning of the talk, I said that the traditional algorithms, they are very easy to code. A compositional algorithm is a little bit more complicated than that, because we need a code structure that is flexible to use different components at the same time. But this is kind of hard to do because many researchers don't use a standard coding pattern. So even if you look at the code, when the code is available, it's hard to just copy the code of the component and put somewhere else. So this is a work that me and Felipe did between 2017 and 2018. We created MOADR, which is a package that implements MOAD in this component-oriented manner. And of course, that's the problem. Our framework is the last one. And then you look at the internet and you're going to find like 10 different frameworks. But it's good to start doing things a little bit more following the software engineering parts. Oops. So just talking a little bit about MOADR. MOADR is an R package. We can even find it in Chrome. And it implements Similarity following the component-oriented design. And the main idea is that we take the MORT and then we identify what are the components. So here, this is the MORDR algorithm. I'm not going to go through it. But these comments, these are the parts that we can exchange the component with something else. And for each of these, we define a parameter. And in that parameter, we have the value from many different papers. We divide these in three parts. So some components are related with the decomposition, some components are related with mutation and update, and some components are related with how you identify the fitness. So now you know if you read a paper and you want to add a new component, you know if you should add in the first part, in the second part, or in the third part. And let me just mark this. So first part, second part, third part. And this is a list of components. So for instance, for the composition method, we have 3, and these come from different papers. For aggregation functions, we have 5. These also come from different papers. For variation operators, we have 9 different variation operations. So you can, like, using this package, you can implement almost like 20 different papers about MORDR by just changing the parameters. And it's an expandable package. People can add more and more components. So that's one way. That's one way to do automatic definition of algorithms. What is the problem with the component approach? The problem for the component approach is that the structure of the algorithm is fixed. For instance, in the MORDR, you're going to always have one set of vector adjustments. You're going to have one set of fitness. You're going to set one set of constraints. But what if you want to explore different structures of your algorithm? Well, you can do that using genetic programming. Genetic programming is related to evolutionary computation, but instead of generating the solution to a problem, it generates a program. And we can use genetic programming to generate new heuristics. Now, genetic programming requires operators. And in these operators, we can put the components. So instead of components being like just a set of parameters that you change, now the components are the operators the genetic programming uses to create a new meta-heuristic. Okay? So we use genetic programming to generate a new program. There is a big problem though. Genetic programming has difficulty with programs involving loops and complex data structures. If you worked with genetic programming, you probably heard of this. It's very hard to do a good genetic program with things that require like recursion. And usually when we want to do like free-form programming, we want to use recursion and loops. So what can we do? There's a lot of research on this. I'm going to introduce the work that I did with one of my PhD students, Pereira, and Bogdanova, which is another professor here. We did this in 2019, and we used grammatical evolution, and we tried to generate a grammar that could create variations of PSO. So here we had a grammar that described PSO, but then we made the grammar more flexible so that it could change how PSO is calculated. So what is a grammar? Okay, the idea of a grammar is a structure that can define commands, loops and recursion, and conditions and top conditions. And then when you expand the grammar, you have a sentence, which is actually a program that can have a loop inside or that can have a comment inside. Of course, it's still not absolutely free form, but it's a little bit more flexible than just changing parameters. And by the way, this is the entire definition of grammar. I'm not going to go over this, but for those who are not familiar, this is how a formal grammar works. This is a very simple formal grammar. In a formal grammar, we have a start symbol, which defines the general structure of the program. And the start symbol goes into other symbols that we can expand. So an S can become an A, or can become A times A. And then an A can become A plus A, can become A minus A, or can become a B. And a B can become an X, a Y, or a B times B. And you can see that this definition is recursive. Because this definition is recursive, we can generate a very wide variety of programs. So for instance, using this grammar, I can generate this program Y. Y is S become A become B, A become Y. So here's the program. Or I can have this, X plus X minus Y. So S becomes A becomes A minus A. The first A becomes A plus A, the second A becomes B. And then this A plus A becomes B and B. Now, two of the B's become an X, one of the B becomes a Y, and we have this, X plus X minus Y. Or we can go all the way here, and this one you can test by yourself. You can use this grammar to generate this expression, Y minus XY plus X minus YY. So formal grammars are very, very powerful. Okay? And in our paper, we showed that we could use a formal grammar to define a PSO and use that to generate variations of the PSO like this. So I'm kind of running out of time, so it kind of worked. We found good grammar. And the really nice thing, the thing that really nice is that by using this grammar, we had some crazy algorithms that like did something 3 times and then skipped some parts. So there are some very interesting algorithms to look there. The problem is that grammatical evolution is very slow, very, very, very slow. Like just to run it one time, we needed to run the computer, let the computer run for an entire day to get one algorithm. But that's cool. That's how it begins. It begins slow, and then people make it faster. There's also some difficulty choosing the fitness function. So we try to write a second paper on that. This is something that is still open. And also there's the problem of how to choose the components that we put there, especially if we want to go do things that are not similar to PSO. Okay, so if you were paying attention to what I was saying, you see that both doing composition based on parameters or doing composition based on GP requires us to choose components. Choosing components is not actually it's not that simple. It's actually a pretty complicated problem. So how do we choose the components? How do we get all the components that we want to do our programs? Well, the obvious way is to look at the algorithms and extract the components from the algorithms. But that's not a very good answer. That raises many questions. there are so many algorithms, and how do we know which of them are similar and not worth studying, which of them are worth studying? Which algorithms are more efficient or less efficient? We want to extract the components of the efficient algorithms, right? And if the algorithms use different languages, and I'm not talking about computer languages, I'm talking about description languages. If the algorithms are describe the same thing in different ways, how do we know if they're similar or not? So what I want to talk in this last part is the idea of measuring the similarity of algorithms. We want to measure the similarity of algorithms because, first, if the algorithms are similar, if we found a group of algorithms that are similar and is very effective, this means that these algorithms might have good components. So we can open them and take the components and use them for our own purposes. On the other hand, there is ensemble methods that use algorithms that are very different together. You get many algorithms different, you put them together, and if all the different algorithms give the same answer, that means that that really is a good answer. If they give different answers, that means that actually there is no good answer. So we can use these algorithm similarity measures to do ensembles. And let's say that we have a problem that no algorithm solves this problem, but we're choosing new ones. We want to choose new ones to try on this problem that are not similar to the ones that we already tried. So we can measure the similarity to see if a new algorithm is really new or is it similar to what we have already tried. Now, in the literature, there's a lot of work on measuring similarity, especially for Metaphor Heuristics and SPOs. We have Loans in 2014 that define strategies or different strategies in SPOs that you could use to analyze if two algorithms are similar. More recently, ARMAS used these strategies to make like descriptions of algorithms. And by comparing algorithms with similar descriptions based on these strategies, they could say which algorithms are similar or not. The problem with these approaches, although they are very, very good, but the problem is that they're still manual. You still have a human looking at the two algorithms. So we want to ask, can we do this automatically? So the last work I want to introduce today is a very recent work that my student Jair, he just presented last week on Bioma, which is automated similarity analysis of these algorithms. And the idea is that we use the same ideas of loans and ARMAS, but we want to automate that. And the question is, what criteria do you use? The key question, what criteria do you use to compare the algorithms? The key idea that we want to do is to cluster different meta-heuristics. So we want to cluster PSO, D, GA, ants, bees, zombies, cats, and then we can look which algorithms fall in the same cluster, which algorithms fall in different clusters. The method that we presented works like this. We generate several variations of the same algorithm by changing the parameters, and then we evaluate them to obtain the features, and then using these features, we generate the clusters. Now, the key idea here is the idea of performance profile. The performance profile of an algorithm is when you get an algorithm and you test it on many different problems, and the performance of the algorithm in each of these problems will make a vector which describes the algorithm. If the problems that you selected to compose the performance profile are different enough, it will be possible to use this performance profile to say that, for instance, PSO is different from differential evolution, is different from genetic algorithms. And then we use this function to calculate this difference, the performance similarity. So in our current results, we managed to find something very interesting. For instance, PSO is very interesting that when you change the parameters of PSO, it clusters very badly. And this indicates to us that maybe PSO is very sensitive to its parameters. On the other hand, FFA, a different algorithm, it clusters very good, which means that it doesn't matter if you change the parameters, the algorithm doesn't change. And then we can see here, like which algorithms, like we have all the FFA and the ATA here, We got PSO over here and over here. We got D cluster here. We got REO cluster here. So we can see that we can cluster the algorithms, and then we can start to see which algorithms are similar and which algorithms are different. There is still a lot of limitations though in this work. This is still ongoing work. So for instance, we chose some metrics, but maybe we just chose like the final result of the algorithms. But maybe there are other metrics that we can use, like how long the algorithm took to solve the problem, or what was the robustness of the algorithm on that problem. So all these metrics could be used to tell if two algorithms are similar or not. And also how to select the functions. We choose some functions, but is that the best way? Are these the best functions to choose? Or is there a better way to choose functions? And this last one is something that I'm really excited about, which is we don't know if, while everyone is using the same benchmark functions, they have some very nice mathematical property, but there is no real proof, there is no real evidence that these are the best functions that can be used to differentiate the algorithm. But now that we have a methodology to say that if the algorithms are similar or not, could we use this methodology to generate new benchmark functions, to try new benchmark functions that really differentiate the algorithms? So can we generate the benchmark functions automatically to maximize the difference of the algorithms? That's kind of a crazy idea, but it's something that that I think it's a really cool idea to try. All right, so that brings us to the end. Given that we started a little bit late, I think we have about 5 minutes for questions and stuff. Just final message of my presentation. So evolutionary computation solves a lot of problems, is a very cool method. But because there are many different problems, we want different algorithms for different problems. However, we need to create this carefully. We don't want to create algorithms that we don't understand. We don't want to create algorithms that we cannot compare. We want to create algorithms that are recombinations of algorithms that already exist, so that we can use theoretical tools to compare and combine these algorithms. So what I recommend is like using component-oriented design. Bring software engineering to our laboratories and define algorithms that are based on well-known components using well-defined structures. Of course, this is hard. There are lots of challenges to be done on that, but it's fun. It's fun to program, it's fun to think about, and it's fun to mix these things and see what crazy new algorithms, crazy but mathematically well-defined algorithms that we can do. Thank you very much. I hope you enjoyed the lecture, and the material is online. Let me know if you have any questions.
Okay, thank you. Let's